Hello viewers, my name is Subh Bhattacharya and I'm based in the United States. I'm the lead for healthcare life sciences at AMD. Today I wanted to spend a few minutes talking about diagnostic medical imaging with ultrasound. So among all the technologies used in diagnostic medical equipment like X-rays, CT, MR, etc., ultrasound is the most attractive. Why? Because it's the least invasive in nature. It lacks any radiation exposure and it has the ability to see soft tissue images. But today, medical ultrasound is still very limited in capability for real-time use due to its challenges using sequential data acquisition, low frame rates of about 50 frames per second, and also suboptimal image focus, which can be obtained only at a single depth. So let me explain a little bit more. So in sequential imaging, the complete image is obtained line by line or one line at a time. Each line is scanned by taking a set of points from left to right with a transmitted beam that focuses on a given point. A line at any lateral position is then produced using dynamic focusing during the reception. At the next step, you go a bit deeper and scan again. You repeat the process multiple times to build the full image. So in order to improve the ultrasound image quality, different transmit focal depths are used, and the final image is obtained using a recombination of these parallel images corresponding to the various depths. Now, ultrasound imaging is also limited to the speed of sound, which is 1540 meters per second. So it takes 200 microseconds to get down to 15 centimeters depth and receive the signal back, resulting in 5,000 measurements per second. So you can do the calculation. So let's say for an image with 100 to 200 lines of resolution, this will result in a frame rate of 10 to 50 frames per second respectively, corresponding to 100 milliseconds to 20 milliseconds. So 100 milliseconds, 10 frames per second, 20 milliseconds, 50 frames per second. Now, if you take a real world example, this is not practical because for cardiac imaging, for example, our aortic valves, this switches timings in the range of about 200 milliseconds. Thus, you can only get 10 snapshots. You divide 200 milliseconds by 20 milliseconds, that's 10 of the moving valve, and that's not enough for real-time imaging requirements. Thus, sequential data acquisition is not adequate to achieve the desired frame rate and the image quality in critical diagnosis of ultrasound. Now, market requires nowadays is a high demand for multidimensional visualization, real-time imaging, and also application of artificial intelligence to assist in diagnosis of critical ailments using ultrasound. So one way to solve this is to use more advanced futuristic techniques called ultrafast techniques. Now, these ultrafast imaging techniques like plane waves of synthetic aperture. So instead of using normal sequential acquisition, it does complete parallel acquisition of the whole plane using either spherical or plane waves. So this way you can produce optimally focused images everywhere in the image and obtain thousands of images per second. So result is a very high image quality, accuracy, and scan depth. Now, these techniques have been limited to research scanners, have been proved to be really difficult to implement on a commercially viable scanner due to vast resource requirements in computing, the size of the systems, they could be the size of a whole room, or because of immense amount of power dissipation. Now, we started on the project a couple of years ago, and we used our AI engine accelerator IP on one of our high performance adaptive system on chips to solve this problem. This computational engine is a large matrix of SIMD BLIW processors. They're connected in a mesh, all with their own local memory, and can share memory with its neighbor. All of these processors are connected using interconnect built with massive bandwidth of several terabytes per second. So this structure allows for an unprecedented level of parallelism that is required to implement such algorithms. We actually demonstrated a real-world system of full capability of such an ultrasound beamformer at the Radiological Society of North America in 107th and 108th meetings in 2021 and 2022 in Chicago. So the rendering and visualization of these images was done using one of our high-performance GPUs. So we used ultrasound data provided in real time by a wireless probe to show the exact performance. Now, using the combination of these advanced algorithms and the high-performance adaptive computing SoC devices, we can actually now obtain multidimensional visualization in real time combined with artificial intelligence to assist in diagnosis of critical ailments. So thank you very much for your time today. Hopefully that was useful. Thank you.